Yeah, so this is a two-part talk. Hopefully I'll be able to squeeze both parts in. I think there might be both interesting, and at least one of them should be interesting for one of you, for some of you. Okay, so the first part is about how catastrophic can catastrophic forgetting be in linear regression. This is joint work with my student Itai Evron, postdoc Eduard Moroshko, and collaborator Rachel Ward and Nati Cerebro, which was published in Call 22. So first, what is continual learning? For those of you who maybe not completely familiar with this term. So in continual learning, we have tasks which arrive sequentially, each having its own distribution. For example, we have an autonomous vehicle and we're learning a task for it to drive in the morning, and then we want to have a task which is slightly different, driving in the evening and then driving at night. Each task has a different distribution of its inputs. So the goal is to try to learn this model sequentially on each task, and then the other task. And then in the end, we want to succeed all tasks together. So the problem is that upon learning a new task, the performance deteriorates on previous tasks. So there's this nice picture from Colori et al., where if we're trying to fit, for example, here a classification task between two classes, the blue and the red, using this nonlinear separator, and then we're learning another task on a different input distribution, then ideally we like the separator to be able to separate the data on both blobs of data. But unfortunately, because we did the second task without keeping the first task in memory, we might have an issue that the updated decision boundary will misclassify the previous task. So we have this degradation. We want to see how to remove this. So the common research and most publication on this focus on algorithmic and practical approaches for overcoming forgetting. However, what we want to focus here is why do we really have forgetting precisely? And we trying to answer this even in the simplest setting possible, where it seems that this answer is still unclear. So what is the simplest setting possible? Well, what we can think of, the basic example every machine learning course starts with, SGD or gradient descent even on linear regression. And we want to understand even there the basic questions. Can forgetting become catastrophic? Meaning if we fit sequentially to the task one after the other, won't eventually be able to fit all the tasks? Is it possible that we'll have this catastrophic forgetting, that we don't fit all the tasks? So just to spoil this lecture, yes, the answer yes, we can find an example, even in linear regression, that this can happen. Is it possible to prevent this without changing the algorithm, just some restriction on the setting? Yes, we show that if we repeat the tasks cyclically or randomly, or even just without repeating them using a randomized order, we can prevent this from happening. How does task similarity, meaning if the tasks are similar to each other or not, how does this affect the forgetting? So this is a bit conflicting in the previous literature. Duan et al. Suggested in a similar linear regression model that if you have high task similarity, the tasks are very similar, this will cause you to have the maximal amount of forgetting. In contrast, Li et al., which was in a different tool layer, a neural network with parallel task last layer in two tasks, showed that intermediate task similarity leads to maximal forgetting. So even though this is a different model, it seems like the conclusion is quite different, which was kind of surprising. So the answer is, can we reconcile these different results? And we show that we can. So we show we can, and the actual answer depends on the number of tasks, and we can get from high to intermediate similarity, depending on the number of tasks we use. So to be formal, let's start with some preliminaries. A continual linear regression, we have a sequence of regression tasks, x1 and y1, x2 and y2 until xt and yt. Large T is the number of tasks. And we want to learn a linear model. W, it's a vector of RD, which we do it sequentially and then succeed on all tasks. We assume the tasks are jointly realizable, meaning there exists some W star, which perfectly fits to all the tasks. For xk times W star, we get the correct labels yk. So the simplest fitting procedure, again, we use is vanilla SGD or gradient descent. we initialize from 0 just for simplicity. And for each iteration, we start from our previous solution we got from the previous task, and then we minimize the quadratic linear regression loss, meaning xkw minus yk, and minimize this with either SGD or gradient descent until convergence. And then we set the solution at the end of the task as wk. And after we keep doing those iterations, after the number of tasks end, we just output our final weight vector. Okay. So what do we want to know? We want to know first how close we are to the solution. What is the solution? So there can be, in at least an overparameterized setting, could be many solutions, meaning all W such that the loss is minimized. It can be 0 if you're sufficiently overparameterized, and if we assume it realizable, it will be 0. So there could be a different type of solutions which minimizes. We want to have the distance to this one of these offline solutions. And forgetting, which is the drift of the previous output. So we have an output in the final task. We want this output on all the tasks, meaning this is a W we get in the end. So the output on all the tasks using the W we get in the end will give us xkwk, which was what we had in the end of the k task. Okay, so this was also a definition of forgetting, just trying to quantify how our predictions have drifted from the previous predictions. Okay, just to note, the definition of forgetting is slightly similar to regret, but it's not regret. Regret is trying to quantify your error on future predictions, not the previous ones. So the solution of this algorithm is simple, right? This is linear regression. We know how to solve this analytically. There is a formula. You can get this in Wikipedia, or it's very, very standard, using pseudo inverse of wk x pseudo inverse yk plus this null space term. And you can rewrite this in a more convenient way, where in each time we do a task, what happens is that the distance from the offline solution, this is our distance, or like the vector of difference from our current W to the offline solution, is multiplied by this projection matrix. We call this pk, is just the null space of each task. And each time we do a task, what happened? We start with the task W k minus 1. We are in some solution space, and then we project using this null space operator to the next task. Okay, this is just algebra of rewriting the solution of linear regression. So once we do this, it's easy to see that when we do multiple tasks, one after each other, we simply multiply our initial difference vector from initialization to the solution by those different projection matrices. So when we do now another task, we again project, and so on and so forth. So what happened, because this is a projection matrix is contracting, it has eigenvalues which are not larger than 1 in magnitude, we always decrease the distance to the offline solution each time we do a task. So it seems that with more tasks, we should converge to the offline solution, right? So it should not forget after we do a sufficient number of tasks. We'll see about that. And forgetting, so what is forgetting? We define this quantity of how well we're doing on the previous tasks. So we can show this bound that forgetting is upper bounded by the average of squared residual, this quantity here. Just take the difference from the last task to the offline solution, and then do the orthogonal projection, the I minus the projection we had before, and we sum over all the tasks. So you can think of it as the complementary projection from P, that we're looking on the residual of our final solution from the previous task. We project back and then see what is the distance of this line from the previous task, and we sum the square of all those lines, we get the forgetting. So this is kind of the geometric view of forgetting in this case. So what can we say about this setting? So the first result is that forgetting, even though we are contracting and always decreasing the distance to the teacher, you can construct an example where catastrophic can be forgetting can be catastrophic, meaning arbitrarily bad. Specifically, we can construct a series of tasks we showed here in this picture, where both quantities are arbitrarily bad. The distance to the teacher and the forgetting are both can be arbitrarily close to 1 as the number of tasks go to infinity. The type of intuition we get for constructing this example is we have to keep a lot of tasks close together in the beginning. So we're doing a projection each time only on the circle. So each time we're not actually contracting a lot toward the center. And in the end, we do larger jumps. And when we construct it in the correct way, we can get arbitrarily close to 1 in our forgetting in the end WT. So this can be arbitrarily bad. Even a linear regression can be catastrophic, forgetting. Can this be preventing if we restrict our setting? So let's look at the first suggestion. How can this be prevented? Repetitions. So what do I mean by that? So if you're in a cyclic setting, for example, tasks often in realistic setting can occur naturally in cycles, such as day, evening, night, as we mentioned earlier in autonomous vehicles. And if we have this repetition, then each time we have a projection to that task, and then we get the same projection again after a while. Okay, so after n cycles, we have what we get here is kind of a cyclic operator. We have the product of projection for one cycle, and then we do this to the power of n, which is the number of cycles. So this, if we can write it this way, this is actually a special case of the literature of alternating projection, which is well studied in functional analysis for the last, 60 years, or even more. Von Neumann is the paper there. So this is well studied. So let's see what we can say about that from that literature. So let's look at the simplest example of two tasks and what we can say there. So we have two tasks. We have one task, and when we project to the second task, and then we project back to the first task again, and so on and so forth, until eventually it seems like we should converge to the teacher in the end. So the theory of alternating projection, it's easy to see that this distance to the teacher, which is just the norm of the teacher times the projection matrices, this power of n, you can upper bounded by the spectral norm of this P2, P1 to the power of n, which under some scaling assumption that the norm of your teacher is not too large, bounded by some constant 1. And this was already solved exactly, and you can find an exact expression in it using the smallest principal angle between the tasks. This is this tau f. In 2D is exactly this angle we have here. In higher dimension, it's the smallest principal angle. So you have this cosinus, the square of the principal angle to the power of 2n minus 1. So the problem is that this convergence rate can be arbitrarily slow. If tau, this angle is going to 0, then its convergence rate can be very, very slow. In contrast, if we look on the forgetting, which was not in the projection, alternating projection literature, we get a different expression. We can bound the forgetting using this maximum I over principal angles. And we get this different 1 minus cosinus square here, multiplying this cosinus square to the power of n minus 1. And this product here is making a very important difference because these all two principal angles appear in both sides. When we optimize this and finding the worst case theta, we get an upper bound which is universal, meaning for all theta we can show the forgetting is actually decreasing as here 1 over n with some constant. So it means that forgetting will not be arbitrarily slow in contrast to the distance from the teacher. So just to visualize this, is this upper bound we have here. This is the blue line. This is the number of steps, and this spectral forgetting, this bound we have here for forgetting. And for different theta, different principal angles, we see that we get exponential decrease in the forgetting. But as we go farther and farther away, we can get you can use different theta to get worse convergence. But this upper bound, which is polynomial, or sorry, power law, will get us the sharp upper bound on all those different exponential convergences. Okay, so it's nice we have this universal bound. And just another thing to say that without repetition, if you just look at two tasks, then we can use this bound and see that, analyze it and say exactly how does the theta affects the forgetting, or how this is theta, this is kind of the similarity between the tasks. And we see that the forgetting is 0 if we have theta equals 0 or 90 degrees. And for two tasks, we get the maximal forgetting, the worst case, when we have intermediate similarity between the tasks, an angle of 45. However, if we increase the number of cycles, we get smaller and smaller angle for the worst case forgetting. Okay, so this is kind of maybe explaining the previous result in the literature, where some works said that intermediate similarity is the worst case, while others said that you actually need high similarity, meaning small angles. Okay, so we have also another more precise results for even generality, not just two tasks. We can show that forgetting after n cycles for a general number of tasks is upper bounded by this bound, which is the minimum between something which is the n to the power of 0.5 with t, and another one which is better dependence on n, but it has the dimension here. Okay, so this is one bound, and another bound we can show with random ordering, not cyclical ordering, either with or without replacement, that the expected forgetting after k task is 9 to the d over k. Okay, so the forgetting again here is the expected forgetting is decreasing to 0. There's no catastrophic forgetting possible. And because this does not depend on t, and we can do this even without replacement, then this actually holds without repetitions. It means that if we do random ordering of our tasks, even if we don't repeat them, we prevent catastrophic forgetting, which is nice. So what about empirical results in neural networks? This is actually similar to what we say here. So there was a recent paper scaling the number of tasks in continual learning that showed a similar phenomenon. What they did is they took each task, you sample two random classes and you sample data points from those classes. For example, here the blue and the blue and the red, the yellow and the green, and so on. Each task is a different combination of two classes, sorry. And in the end, after some time, you just check the performance on all classes together. This is the test set. And they used vanilla SGD in our other algorithms as well, but even in vanilla SGD, what they show that you can learn quite well all the tasks together, meaning the test accuracy is not so bad on a variety of benchmarks, which are popular in the continual learning literature. Okay, so just to summarize this part, what we show that even a linear regression forgetting can be arbitrarily bad or catastrophic, and there can show the precise exact effect of task similarity on the forgetting between tasks. And we can show that with cyclic or random ordering, forgetting diminishes linearly with the number of seen tasks. Other things we mentioned in the paper, but I didn't have time to talk about here, is we find conditions for zero forgetting, more general than what we mentioned. Even we can find lower bounds on the rates, and discuss relation to other quantities such as regret, catch-match method, alternating projection, stochastic proximal point algorithms, NLMS, and many more. Okay, so thank you. If you want to read, there's an archive. Also, it's on Colt. Feel free to ask many questions in the end. And now to the second part of our talk. This part is about the implicit bias of minima stability. It's actually a combination of a couple of papers. The first one was with Roto Mulayov, Tom Michaeli, the implicit bias of minima stability of view from function space in NeurIPS. And the second paper, we had also Mor Spiegelnax, my student, and Greg Unge joined us, and this is currently under review. So our motivation for this work is trying to understand the behavior of neural networks in overparameterized regime. So if we have data points, here it's just the univariate data from X to Y, and we want to fit it using a neural network. then we can get one solution or a different solution or third solution, a different interpolating solution. And the question is, to which solution does the optimization algorithm converge to? And so there are quite a lot of works about this. It's usually one of the ways to call this is the implicit bias of this learning or gradient-based method. One of the first conjecture was this implicit bias is a kind of regularization that also might be useful for generalization. And this was proven, this behavior that gradient descent has this implicit bias in several cases. The simplest one is just very trivial linear regression, under some assumption matrix factorization, also with linear classification, logistic regression on separable data, and many other works afterwards. And the limitation of this is that this usually relies on some manifold property, as shown in Azoulay et al., which does not always hold. So we can show examples where the conjecture breaks, that we can't really get some form of regularization from a gradient descent, for example, for a single ReLU or for a matrix factorization problem. So another issue that all of those works I cite here and even other below usually assume a gradient flow, meaning vanishing step size. And if they don't, they assume the gradient is small enough, so we're close to gradient flow. So we can't really say much about how step size is affecting the implicit bias. However, there is a large effect of the step size, as we show in this example. We use a single one hidden layer neural network with ReLU network, and we look at the loss when we train the network. It goes to 0. In the end, we perfectly fit our data points, and we get some function, which is this black line. And now we try a different experiment where we stop training at some point, increase the learning rate, and then continue training with this increased learning rate. What we see that we again perfectly fit the data points. However, we converge to a very different solution in which we actually are much less sharp in the function space, in the predictor, than the small learning rate behavior. So this interesting behavior could be useful also to understanding what happens in neural networks and their generalization, because it seems that high learning rates, of course, are needed in many cases to get good generalization behavior in practical neural networks. So in this work, we're trying to understand how a property of SGD stability, which always holds, don't need to assume it, can explain this type of implicit bias, and how can you connect it to the step size, how the step size is affecting the solutions we get. So to understand what is this stability of SGD, so suppose we have two types of minima in parameter space. One is flat minima. So when we do gradient descent, we converge to this minimum quite well. However, if we use the same learning rate, if it's too high for the sharp minima, meaning even the same learning rate can be too high for the sharp minima, we will not converge and escape exponentially fast from that minimum. So we call this flat minima stable because we can converge to it. And here, the other one is unstable. So for gradient descent, the condition for being stable is sufficient and necessary. It means the condition is that the maximal eigenvalue of the Hessian is smaller than 2 over the step size. For sharp minima, which are unstable, this is larger than 2 over the step size. So this is a necessary condition for SGD, but again for GD, it's also sufficient. So what can we say using this relation? So we can derive here, what I'll talk about is deriving a framework for analyzing, this I will not talk about, it's in the paper, analyzing stability of non-differentiable minima switching systems, and show that large step size lead to smooth functions, meaning specifically smoother near the center of the training distribution. And we verify this behavior experimentally. So in this talk, I will talk about the part which is differentiable, right? Because ReLU functions are actually non-differentiable. Some subtle issues about discussing stability with non-differentiable functions. However, this is more complicated, so I'll leave it for you to see in the paper. I will talk about the second and third part. First, we focus on the simplest setting of a not only shallow one hidden layer value network, but even univariate, meaning the input is scalar. Okay, so we multiply it by weight W and add the bias B, and then the value, and then multiply by another weight to add the bias B. So this is our predictor function. You can write it this way, and we sum over all neurons. So this is the ReLU function, and we look at the family of functions that can be expressed using this way, using k neurons. So this is just a family of piecewise linear functions which has k knots, meaning this non-differentiable changes in the slope. So we minimize some loss function. We focus here on the simple mean square error loss. This can be generalized, but we focus in this case for simplicity. And in the overparameterized case, the number of neurons is larger than the number of data points. Then this loss function can be minimized. We can fit perfectly all the data points using our neural network and get zero error. However, there are infinitely many solutions, right? We are overparameterized, so we can set the neurons and parameters in the different values and get this zero loss. And we want to understand what is this, what does it entail that we arrive to this minimum. However, when we are at some minimum there, we get some predictor function, and this predictor function can have two different implementations, meaning we can use different parameters to create the same function. With one implementation, we can get a sharp minimum in parameter space, and another implementation, we can get a very flat minimum in parameter space. So if we want to understand how this stability affects the predictor, we need to find what the implementation exactly we're talking about. So to do so, we define the space of all parameter vector that implement the same function f as this omega of f. And we look at the flattest implementation, meaning looking over the maximal eigenvalue of the Hessian, we take the minimum over all possible implementation for a given function. Okay, and now we would like to bound this flattest implementation, this stability, and we will show why this is useful. So our main result in this paper is that we can lower bound this flattest, the sharpness of the flattest minimum, meaning the maximal eigenvalue of the Hessian in the minimal case. And we can lower bound it using 1 + 2 times this integral of the absolute value of the second derivative of the predictor times some weighting function g. Okay, so some property of this g, I will not write it, it's a bit complicated expression, but it's in the paper. It's a non-negative function which depends only on the data set. The data set meaning just on the data point, there's nothing else that goes into it. And most of its mass is usually located in the center of the data set, and it vanishes outside of this data distribution. And we have this closed form for g. It's an exact expression, just pretty long. And why is this useful, this result? So this is the function g for some specific data set of uniform data. This is useful because we know that for stable minima, we have that 2 over the step size is larger than the sharpness, meaning the maximal eigenvalue of the Hessian. This is true also for the flattest implementation. And this entails that this expression, which kind of is kind of a norm on the predictor, is smaller than 2 over the step size. So as the step size will increase, this expression must become smaller and smaller. And this here is a second derivative, integral of a second derivative. You can think of it as a weighted L1 norm of the second derivative. And the second derivative here is in the weak sense, meaning it's a non-differentiable function, so it will be a delta function if we differentiate this value. So what do we get from this? So if f is a stable solution for SGD with some step size eta, then we can say that this expression is smaller than 1 over eta minus half. And this is when you change the step size, this will make things smoother or less smooth. So we assume for this theorem that our solution is twice differentiable, meaning the kinks of the value function are not falling exactly on the data points. Otherwise, they might be non-differentiable, and then we need to do some correction, which is in the paper, what happens when the data points and the kinks fall on each other. Okay, so we get a slightly different expression. And just to show to visualize our results, so here we show the data points and we fit some function first with a small learning rate. It's 0.0001. And again, we fit perfectly the data points, but the function is quite sharply changing. And here we plot in black the absolute value of the second derivative, meaning kind of how smooth the function is. And again, we see it should be quite strong. And in red, we show this G function for the data set, which we can calculate. And what we see that even at small learning rates, this G function seems to have some influence and causing the sharpness to decrease around the center of distribution. It's sharper around farther away from this center. As we increase the learning rate, the function becomes less fluctuating, smoother in some sense. And you can see this in the second derivative of the function. And again, it's smaller near the center of the distribution. And if we increase the learning rate even higher, we get even a smoother function. And we see that even for high learning rates outside of the distribution, we get still some fluctuation, meaning that farther away from the farthest data points, we do get some sharpness. So this matches our results. Okay, and now let's compare all the different bounds we had. So first we have 2 over the learning rate. So this is the learning rate in the x-axis. And if we examine the sharpness or the lambda max of the Hessian at convergence, we get often that this is equal to 2 over eta. Even though it should be bounded by this, it's actually, we see empirically that it's equal, and that's a phenomenon was called the edge of stability. The paper, for example, at Cohen et al. And this kind of tightness says that this part of the bound at least is very tight. Now we want to see what happens with the flattest implementation, not the exact implementation we converge to, but the flattest implementation for that function. And we see this has some slackness from the bound. And then we have our bound, which is even farther below that bound. But it seems that they're all lower bounding in the right direction, as our theorem says. And interestingly, when we get to high learning rates, the bounds actually become much closer. And we can show that this seems that it actually becomes a very tight characterization of the predictor. Okay, so far we talked about univariate neural network, meaning functions that are from R to R, but we're more interested maybe in multivariate inputs, neural networks. And in that case, can we say something about the implicit bias? So this is expression we had for univariate neural networks. And now the generalization of this is something which seems similar. So instead of a second derivative of the function, a scalar function, we get the Laplacian of the function, meaning the trace of the Hessian from the predictor. And again, we have the absolute value of this, and rho is some density, which is it can be calculated. It's defined as some transform, inverse Radon transform of some well-defined function, which again depends only on the data set. And this is smaller than 1 over the step size minus half. So we call this interval here the stability norm. We have different forms for this in the paper. This is one perhaps simple form. And just try to understand what's going on. So we have some function. This is a function, a 2D function here from, we have x1, x2. So it's piecewise linear because they are, because it's made up of values. And if we take the Laplacian of this function, we get kind of 1D, like line, which are delta functions on a line. And the data points here are in blue. And now we need to integrate those lines with this raw function, which we can we visualize this raw function for this data here, and we get the stability norm. Okay, so we get a more complicated expression, but it's still useful. So what can we say? So first, it seems that again, that if we have a larger step size, we get a smoother predictor. Okay, so we can see this again in 2D, that small step size get wildly fluctuating predictors, which perfectly fit the data points, but have those sharp peaks and valleys. And if we increase the step sizes, become more calm and eventually much flatter. And other implication is we can show that stable, meaning shallow neural networks which converge to stable minima, are not universal approximators, in contrast to standard one hidden layer shallow networks, which are universal approximators. So what do I mean by that? Consider this function, this pyramid function. It's visualized here. And this function, it's easy to show. It can be represented by a two hidden layer ReLU network. When you train it with finite step size, it can show also it's a stable solution for this two hidden layer ReLU net. However, we can show that this function has infinite stability norm, meaning with one hidden layer, we cannot approximate it. If we're trying to converge with any finite step size, we'll not be able to converge this to a stable minimum. So it seems this depth separation between one hidden layer and two hidden layer using stability. So what can we say? What can stable shallow neural network can approximate? Well, if they can't approximate this function, so it turns out, and there are more details in the paper, that you can approximate sufficiently smooth functions. Specifically, they have a bounded type of a weighted Sobolev norm. Okay, so those functions you can approximate using a stable one hidden layer neural network. Okay, so to summarize this part, second part, SGD converges to stable minima, and stable minima, due to that, and use this property to show the stable minima become flatter as the step size increase. That means become flatter in predictor space, and they are flatter in function space. In parameter space, and this parameter space flatness corresponds to smoother functions in predictor space. Okay, so that's very nice, but can this lead also to better generalization? So empirically, if we check this, so what we look exactly, we do this first numerically, of course. So here's a simple example in MNIST, where we show our bounds are actually quite tight. This is our purple bound is our final bound. We see it bounds the sharpness and the 2 over the learning rate. And we get that as we increase the learning rate here, this is a specific setting we chose with high initialization, so we get bad performance at small learning rate. However, when we increase the learning rate, we get a much better performance. Okay. So it seems that this learning rate effect can actually improve generalization in this case. But can we say something theoretically about generalization? So for neural networks, it's a bit tricky at this point. So I'll go quickly about the work. We did this on a linear diagonal neural network, showing how implicit step size is affecting generalization. This is joint work with Moore, Spiegel-Naxon, Kaviar Vachindran, Nati Cerebro, and myself. So what is a deep linear diagonal model, or a deep linear diagonal neural network? So this is just a model. It's a linear predictor, X times B, where the weight matrix is parameterized by these parameters W to the power of D. And we usually have W plus and W minus, so you can represent both positive and negative numbers even when D is even. So what we show for this specific model, if we use we assume we converge to stable minima using a SGD, then we can show this type of expression, this norm on the predictor is bounded by 2 over the learning rate with this constant, D squared. So what does this expression means? It means that we have a bounded weighted 2 D times D minus 1 over D norm. Okay, so as we change the depth, this will get a different norm. Specifically for D equal 2, and if we assume that the mean of the data is non-zero, meaning we have a non-centered data, this gives us some bounded weighted L1 norm. And this is kind of similar to the RIT regime, which was discussed in previous papers, which is different from the kernel regime. So you can't describe this minimum L1 solutions using a kernel. So it's a different regime which was considered rich and can get us good generalization in at least this model in sparse regression setting. And this was kind of an analog for the rich regime in neural network. We get better generalization when they're far away from the kernel regime. So specifically, we examined the sparse regression problem with X sampled from this Gaussian, non-centered Gaussian distribution. Y is some k-sparse predictor operating on this each data point. And as we examine the generalization and the test loss, and we change the different initialization scales and the learning rate. So if we look at the smallest learning rate, this is the top curve here, we see that for very small initialization, we get good generalization, small test loss. This was shown that for gradient flow, exactly we have this exact result. We minimize the L1 norm for vanishing initialization scales. And however, for large initialization scales, we minimize the L2 norm of the predictor, and we get, in this case, in sparse regression setting, we get not so good generalization. However, in this setting, we show that when we increase the learning rate, we get the other lines here, which become more and more lower, meaning we improve the generalization until with a sufficient large learning rate, we get close to the L1 solution, meaning a good generalization. And specifically, we can show that we can get low population loss in this sparse regression setting if we have a sufficient number of samples, which is k, meaning the number of sparseness, time polylog d over delta. And this is some probability 1 minus delta. So as long as mu, the data is and not non-center, meaning mu is not 0, and d equals 2, we get generalization with similar to kind of L1 regression setting. Okay, so that's it. Thank you very much. I'll be happy to hear any questions if you have.
Hi, thanks for the great talk. How high can the learning rate go then?
In which model?
So you have a lower bound, which is the second derivative integral.
Yeah.
How high can you keep increasing the learning rate to keep getting better
performance? So until you get to the flattest possible minimum, right? There's no infinite number of flat. You can't get like infinite flatness, right? So eventually you get some minimum, which is the flattest possible, and then you can't increase the learning rate anymore because you won't have any stable minimum to converge to.
Is there some sense in which how this depends on the architecture?
I guess it does, but I don't know how. Like, sounds like maybe a difficult question, but interesting question.
Just a sec, we have one more.
Thanks for your nice talk. I wanted to ask about the activation function. So your talk was about ReLU, and I'm wondering where in your analysis you use ReLU, or does your analysis really apply for any activation function?
Well, I guess you can use ReLU or leaky ReLU, but
like, are you using homogeneity somewhere in your argument, or? So
it's in the in the proof. When you prove this bound here, you need to use a specific. You just rewrite the specific form of the Hessian with the ReLU, and then we bound it because of use the form of the ReLU to. If it was the ReLU, I think it would be at least not using our technique.
So, like, if I wanted to do this for tanh, would the same thing hold? Just this formula would become a little bit different?
I don't know. I don't know exactly how to do this for tanh.
So there is something specifically about ReLU that you need?
ReLU or leaky ReLU, yes, for this.
is it possible to describe what it is that you're using, or like what's the essential thing that you need for your analysis to work?
It's just something that in the form of the Hessian that you get those indicator function from the ReLU, and then you can use them to do those averages of the data.
Okay.
I think it's harder to do this because then you would get something which is okay. So in the end, you want to get something which depends on the predictor. But for ReLU, the predictor is it has like the second derivative of the predictor is just a sum of the delta functions times the weights, like W1, W2 times the delta function. That very simple form does not hold for other types of.
Okay, that's very helpful. And related question, the part that was co-authored with Greg, where you have this omega of f, if you take tangent, does that omega of f become a single point and you no longer have this ambiguity?
I think with tangent there's this, it's an odd function. So you have this ambiguity of plus minus 1, right? You can multiply the output.
Yeah, but that won't change the flatness, right, of the...
No, it's not change the flatness, just different minima of the same parameterization. So there is ambiguity in the... So you're talking about the univariate case or the multivariate
like in
case?
any case, is it the case that if you move away from ReLU, then you no longer have this implementation ambiguity?
Okay, you have this, yes, because of them, if you homogeneity ambiguity, I think there's another ambiguity I'm trying to remember. Because you can switch, like, you can have different, okay, so you can have like several ReLU together in the same point, right? Division exactly the same. So how many, right? The same function you can implement it using like 2 ReLUs on the same point or one.
I see.
Right? You can decide how many ReLUs you assign to each kink.
Yeah. Okay, thank you.
You're welcome.
Yeah, just 1 second.
I was wondering what this analysis say about how we decay the learning rate over time. So should we decay it and then suddenly increase it so that we hopefully settle down on a stable minima? And secondly, this bound was for a particular lambda, right? So if we have a schedule for lambda or a decaying schedule, can we have a similar bound for the eigenvalues? Or
Sorry, can you repeat the second question? I didn't follow.
So the bound that you have, this is for a particular learning rate, right?
Yeah, this is the analysis I showed you. It's for a constant learning rate. Yes.
Yeah, so I was wondering if that can be extended to a schedule of learning rate where we either increase lambda over epochs or decrease the learning rate.
Yeah, so we analyze here not the dynamics, but the minima we converge to. So this is the step size required for the minima to be stable. So I'm not sure exactly how to, what would the schedule here mean? Like, how do you define the stability of the minimum with schedule? Mm-hmm. So empirically, there's some work, I think there was a Gilmer that showed that if you use, for example, cosine decreasing schedule, then eventually you converge to this, the decrease of the learning rate in the end, it doesn't change much your sharpness. Okay. You're still staying close to this high learning rate sharp minima. It's an interesting question, how far will it go? Like if you do for a long time, very small learning rate, you would probably go away. again, if you do SGD, I guess. But if you do like sufficiently fast decreasing learning rate, then like the cosine, I guess you would stay close. So I guess, again, it depends on the types of, like if you use SGD or GD, it's a very interesting question, but I don't think it can be answered directly with the analysis here. You need to consider the dynamics.
Okay, thank you.
You're welcome.
Really great talk. I have a couple of questions. The first one is pretty much the same one that was just asked. So suppose I wanted to use this result to set the step size. And so the analysis is made for a constant step size, and this gives me an upper bound of the largest step size that I can choose. But to compute that upper bound, I need to know f, but I'm actually learning f. So how do I use it in practice? And I guess connected to the scheduling question, I could use it because I have a current guess of f, and I could use that to select the current eta and then keep changing it. So therefore, two entangled questions. How do I select eta, given that I don't know f in the eta constant regime? And doesn't that immediately lead to a schedule, given the current estimate of f?
I see. So you're saying you should try to estimate f currently, and if you're not satisfied with the flatness, you should try to increase it, and something like this, right? And trying to follow your suggestion.
Yes, I'm saying that this gives you a formula to compute the upper bound on what eta should be, and to compute that upper bound, you need to know f, but you don't.
You need to know f. Yes. So you have f is your function, the predictor of your neural network currently. So you have it, I guess.
But that is changing with the parameter, no? Or not?
Yeah, it's changing, of course. But like your current f, if you're currently at the minima, your current f will determine whether this minima is stable or not. So you can use
exactly
this
that's the problem, that I don't know the true f at which this quantity is true. So how can I use it to set the learning rate? How can I use this result to set the learning rate?
So I guess if you assume you're close to minima, it should be an approximation of the true f, right? If you're far away, it's not very useful.
My other question was about the first part of the talk on continual learning. I think you said that you may not be able to prevent catastrophic forgetting if you just present one task at a time in a fixed deterministic order. However, if you do the cycles or if you do a randomized selection, then you can prevent. I was curious as to exactly, can you explain the intuition as to why the fixed order, I cannot prevent catastrophic forgetting, but as soon as I randomize the order, I solve the problem. It sounds like mysterious as to why that would be the case.
Yes. Yes. So let's look at the specific example we had. Oops, sorry, it's okay. So that was the worst case example where if we don't do anything, like just look at somebody give you a set of tasks and give you this task, and then it's bad, where you will have catastrophic forgetting. So what happens here in this task? Initially you get the black lines are tasks which are huddled together. They're close, very near each other on the circle. So each time you project to the next task, you're going on the tangent direction, right? On the surface of the circle. You're not contracting toward the teacher. And that's the problem. You're constructing, so you're like gliding away until the end, and you don't really contract a lot. But even worse, you construct it in this way that forgetting the sum of all those residual is actually arbitrarily bad to go to one. However, if you take this example and you randomize the order, then this will collapse, right? So, for example, you first start from here and then you go to one of the examples in the end, you'll project quite far, right? You'll do quite a strong retraction, right? From, let's say, if you do from the first task to the last task, then you'll immediately go to the teacher. There will be zero forgetting. You learn perfectly the teacher here, right? If you do something in the middle, you'll just be much faster. So this kind of breaks this carefully constructed example, and when we show this is generally a good way to break such issues and prevent forgetting in the worst case.
And my last thing is primarily a comment, and it's probably a literature that you might be very unfamiliar with, but in the 80s or so in the controls community, there was a lot of research about how do I identify or learn a system, and the question of persistence of excitations of the inputs was postulated as a criteria. In the 2000s, this was extended to switch systems, where you go with one dynamical system, then another, so akin to the idea of multiple tasks. And then the question of how quickly do I need to switch from one to the other came about. And this notion of persistence of excitation, that I needed to do a schedule where I visit all the systems sufficiently often, was sort of the basic criteria in order to be able to learn all of the systems together. So I am postulating that there might be some connections with that, and that might allow it to extend it to the dynamic setting and more complex systems.
Yeah, I think it's an interesting analogy. Yeah, thanks. I'll think about it.
We have time for one more question.
I just wanted to ask if there are similar theoretical results, speaking of the second part of the talk, but not about the learning rate, but about the batch size, if we have some results on the implicit bias of it.
Okay, so for stability, I guess it's problematic, right? Here we just use the fact it's a necessary condition for SGD, so our condition does not depend on the batch size. So it's true for any batch size, because that's why it's a bound. So the question is, maybe you're far from the bound because this becomes like not tight in SGD. So the question is, what is the thing that you're are about? Like if you have some edge of stability for SGD that you're sitting on, I think there was some recent paper suggesting you have some something which like depend on the product of the Hessian and the direction of the variance in this. I forgot exactly how they called it. Which just suggested some other thing and showed empirically that actually you sit on the edge of stability on this quantity, not on this lambda max. So maybe you can analyze this quantity using similar results and get how the batch size is affecting performance. So I didn't do it if you want, but that could be a nice idea.